And we are live. Welcome everyone to another meme lecture. Today we're going to talk about compartment models and linear stability analysis, two key tools to understanding how to do mathematical models in a very broad sense. Let me just triple check that I did in fact go live. Yes, I am live. Okay. Sweet. So now that we're underway, let us begin. So first we're going to talk about compartment models and what they are. Simply put, compartment models will often be used to track populations in a variety of different states. Now, populations can mean all sorts of things. It can mean people. It can mean animals in general and multiple different types of animals. I could talk about chemicals. So a lot of compartment models deal with different chemicals in different states. What's key to understand, the key to understanding whatever you are modeling is that it has a wide range of discrete states that it can transition between, right? So one could even do something like you have a whole bunch of molecules that transition to different temperatures or different positions based on various rules. The key thing is that there's a number of states and you're basically prescribing rules to transition from one state to another. And you can go back and forth, you can have irreversible changes. There's a lot of flexibility into what this means. So a very simple example of a compartment model is to consider the ride queue. Right, you go to some theme park, you want to board a roller coaster of some sort. You're going to start by entering a queue, and you're going to wait in that queue for some amount of time, right? And that time you're going to wait is going to depend on some process. And then once that process is over, you're going to board the ride, ride the ride. Once the ride is over, you're going to disembark from the ride, and sometimes they'll just dump you right off. Sometimes they'll funnel you through a little gift shop. Like where you can get the pictures from the ride. And then after that, you can flow on, go back to the rest of the theme park. If you wanted to get really fancy, you could have a whole bunch of rides connected to each other. But the key idea, though, is that each step of the way, there's a transition, right? There's someone who goes from not being in the ride at all to joining the queue, and that's modeled by process A. And then there's a transition from being in the queue to being on the ride, the boarding process. B for boarding, right? And that's modeled by process B. There's another process to get off the ride. That's going to be process C. And then once you're in the shop or whatever, you can then leave the shop with a process D. And in this case, it's a one-way flow. However, it does not have to necessarily be so, but this is a simple example. And if you want to count the number of people, you're going to have a system of ordinary differential equations, Q, R, and S, that change in time, and that tracks the number of people in these different states, right? And we notice that for every person that leaves Q, they're going to go into R. So in the dq dt, we have a minus b term, and then in the dr dt term, we have a plus b term. Likewise, as you go from R to S, you have a subtraction of C from R, and you flow into S. Now, sometimes you can have a mixture of things. You can have a law of mass action. It basically this is a common way of mixing two populations in two different states to transition to some third state. So a common example of this comes out of chemistry, where you have chemicals A and B that produce chemical D. And they're going to be coefficients, right? You can have an alpha, beta, and a delta that represent the different stoichiometric coefficients in a chemical reaction equation. And from those equations, you can pull out basically a rate of reaction. And what the law of mass action states is that if you have some population A and some population B that need to mix together with those coefficients, is that the rate at which this reaction happens is going to be the population to the appropriate stoichiometric coefficient as an exponent. Right? So in this case, for a chemical reaction, you have some RF that transitions, the rate of F basically transitions from A plus B into a D. You have A to the alpha and B to the beta, and that comes out to produce D delta terms. And then there's usually some other rate coefficient. Often in chemistry it is called K. If you've ever taken a chemical kinetics class, that's what they're often called. And the transitions, though, are going to basically be from A to B to D are going to be RF alpha, or negative RF alpha, negative RF beta, and then you're going to add an RF delta to the dA, dt, dB, dt, dd, dt terms, equations. And this is good if you have interacting things, if you have some interaction. And I'll show an example in a second. And that example is this the classic SIR model. And the idea of an SIR model is you have a population dealing with some disease. Pick your favorite disease. I don't care what it is. Could be Ebola, could be COVID, could be... should I say that word? Am I allowed to say that word? Probably not. Oh, well, goodbye monetization. Could be chicken pox, could be pork pox, could be beef pox, I don't know. I'm making up diseases at this point. So you have some population, and they come in three classes. You have those who are susceptible, those who are infected, and those who are recovered. S, susceptible, infected, I, and recovered, R. And there are different transitions you can have to go from one population to another. So you can be born, and you're susceptible. And then you can get infected, and then you can recover from that disease. Sometimes, with certain diseases, you can lose immunity to that disease over time, right? If you've ever had, you can get, disease can come back in waves or whatever if you lose immunity. Especially, or a new variant might emerge or something, and the main variant mutates, and you are no longer immune to that. But a key understanding of this law of mass action that we care about is that in order to generate new infected people, you need someone who is previously infected, someone who is susceptible, and from that you will generate two infected people. Right? So someone who's infected will transmit to someone who's susceptible, and now they're both affected. And what that means is you have an I plus an S, right? And those leading coefficients are 1 and 1, and then it comes out to produce 2, right? And that interaction is the key driver to transition from S to R. Now, the other transitions from birth and recovery and lost immunity and death, these are going to be merely linear relations. So the more people that are born, or everyone who's born, it's going to be proportional to the total population. The proportion of people who die is also going to be proportional to the total population, though you might have varying rates depending on your interaction with the disease. So, for example, if you have particularly deadly disease, you're more likely to die while having the disease. And even if you're recovered, your risk of an early death might be elevated, and you can model that differently. You can model that accordingly. And that's what we have here. You have all these different terms. So if you have births, those are going to be that purple term. That's going to be proportional to the total population. The death rate, again, as I mentioned, is going to be proportional to which the number of people who die is going to depend on which group they're in, and the coefficients might vary. So recovery happens at some other rate, right? So if you're sick, you're going to recover. You can have a simple model at least of every day you have the disease, 10% of people who have the disease are going to be cured, and that'd be like a 0.1 per day recovery coefficient. You also have immunity loss. So if immunity is lost, you then transition from that orange R state back into that susceptible S state. And then, there's a bunch of additional factors that you could include in such a model. However, these are the most common ones, right? These are, this is like the baseline SIR equation. There's a bunch of others that you can do for other diseases. You can also use it to model other population trends. There was an interesting model I want to investigate at some point involving China's infamous one birth policy, where if you have if you have men and women who can only give birth to one, a man-woman pair only giving birth to one child, and the social dynamics of that, and how that will affect the overall population. Can you model the trend of what the overall Chinese population is going to be? I think that's an interesting question that I do want to probably make a separate video about at some point in the near future. So if you keep an eye out for that, I'll probably make it at some point. If that sounds cool, please let me know in the comments. And while I'm mentioning that, make sure to like and subscribe if you've never seen me before, or like if you have seen me before, and subscribe if you haven't. You can also take compartment models to represent spatial states. So I could be 1 mile along the, if you have, for example, a classic example might be a road, right? You're driving down the road and you have a bunch of different mile markers, like, oh, I'm on mile 1, I'm on mile 10, I'm on mile 11, I'm on mile 12. You can have different boxes or different compartments that represent which mile you are upon. And you have a bunch of different rules that dictate the flow from one physical space to the next. One classic way that or one common governing rule that dictates the transition is the difference between two adjacent states. So if we have more of one thing over here than another, there's a tendency to flow from a greater to a lesser thing, right? So if you have more heat over here, the heat wants to flow to where it is colder. Likewise, if you have a denser population, it sort of wants to diffuse that population density and push people out. And so you have things like suburbanization. And you can model this in a number of different ways, but a common one is to basically say, hey, if you have a spacing, right? If you have a spacing between two populations, H, and you take these compartment models, if H represents the space between the between two adjacent compartments, you can use that H value to basically compute what eventually amounts to a second derivative. And from this sort of a model, if you pick a isometric constant alpha, isometric, is that the right word? I think isometric is a fine term for that. What can happen is if you increase the number of compartments and break the compartments down into smaller and smaller granules, where basically each box X becomes smaller and smaller in an infinitesimal limit, this equation actually turns out to be a heat equation or a diffusion equation. If you have a variation of alpha and beta, you're also going to get a more general diffusion equation. Now, this is a simplest case where alpha that flow rate between one state to the next is constant. And this happens in one dimension, but if you have a more general compartment model, you can use a similar principle to model the diffusion across some sort of network. So if you have you can use diffusion to model the spread of some political ideology or some actual, or again, an infectious disease, if you have a certain network of connections between people. And to do this is usually accomplished using what is called the negative Laplacian matrix of a graph. And that name Laplacian, both here and in the heat equation, do represent that same idea of sort of taking differences between adjacent nodes or adjacent spots or adjacent real numbers, basically. And it applies that same idea to two different scenarios. So you can have something spread out on a graph using Laplace, or you can have something spread out on a real manifold using a different Laplacian that still functions in the same way. So if you ever hear that term Laplacian, it's not always, but it often is going to refer to that idea of a diffusion. Laplace was relatively prolific, so if something like that, if you hear the term Laplace, he could have done other things as well, or it could be some other thing, but it doesn't have to be. And thank you to all who are watching. I see that we have a whole integer number of viewers. An integer, a positive integer even. So compartment models are really cool. They are a great way to set some ideas down. I'll probably talk about some more compartment models that I find interesting in the future. If you have any that you thought sounded cool, besides the one I've mentioned, like the SIR and the Chinese model, let me know in the comments. But then a question comes of how do we analyze such a model, right? So compartment models are a system of ordinary differential equations, right? And we can actually model it using this red equation here. We have a vector of different states, right? You have a whole bunch of different compartments and different populations in those compartments. And you have some transition rule, vector f of vector x. It basically takes that state, it takes that state variable, pushes it into some function, and that dictates how the state changes over time. So all the compartment models can be represented, or at least all the discrete, finite dimensional compartment models can be represented in this fashion. And there's a question, well, how can we understand its behavior? And there's a great quote out there. I do not know who to attribute this to, but it basically says that most of modern math is what we can turn into linear algebra. If you turn a problem, most of the problems that we have a good firm grasp upon basically comes down to, hey, if we can turn this problem into linear algebra, we can get it. If not, maybe we'll get something like an approximate, or we're going to have to do some combinatorics or some weird number theory stuff. But that's complicated and that's hard. So if you can turn a problem into linear algebra, it's great. And what's nice is that most ordinary differential equations can be reduced to some sort of equation of this form, even if you have higher order derivatives. So if you have a second order derivative, you can take that first derivative, define a new variable around that, and then have two equations, one for the first derivative and then one for the second derivative. An example I have here is the oscillator equation, mq double dot plus kq equals 0. We can break that into a q dot equation that defines a new variable p, right? And then we have a p dot equation that defines basically what happens to the momentum of the thing. And that momentum is driven by the position, and the position is driven by the momentum. Right, and they're sort of coupled together, right? That's what makes the oscillator so cool. That's why I always talk about it. If you're sick of me talking about oscillators, you can complain about it in the comments. That's not going to change things. I think oscillators are a great example of basically any ODE, so silence. And what you can do, though, is once you have something in that form, dx dt equals f of x, is you can do an expansion on that f. And you expand it about some point x naught. And then x naught is going to, that's some interesting base point. And you can expand it using what basically amounts to a multidimensional Taylor expansion. Right, so you have a constant term, a linear term, and then a quadratic, you'll have quadratic and other higher order terms. And what linear analysis cares about is it cares about those first two terms. But what's really nice is if you can find a place where f of x naught is equal to the zero vector, i.e. sort of an equilibrium point where things do not change, you're left with basically a linear system of equations. As we see here, and that linear system of equations is defined dy dt equals jy, where J is the Jacobian matrix, and whose entries are basically defined as the different derivatives of the different components of f with respect to the different components in x. And so this is a very nice, useful tool to have. And so we have we have a linear matrix system, right? We have dy dt equals jy. Now the question is, how can we solve such a system? Well, if we consider more broadly just some generic matrix equation dx dt equals ax with some initial condition x0 equals x naught, the simple idea that we can use is basically go back all the way to the first ODE you learn about, and dx dt equals ax, right? And the solution to that is going to be e to the at, right? But instead of just using some real number, a, we're going to now use a matrix A. And we apply that matrix e to the ta to the initial condition, right? The initial condition is a vector, and the exponential e to the ta is a matrix. And that matrix is defined using the Taylor expansion of the Maclaurin series formula for an exponential. So it's it basically starts with a t to the 0 term and an a to the 0 term over 0 factorial. That's an I. That's the identity matrix. And then there's a linear term t times a over 1, and then there's a quadratic term t squared times a squared over 2 factorial, a cubic term, etc. It expands out like the exponential should. Now, the key to computing a matrix exponential is, in most cases, or in all cases, is that a matrix can be diagonalized or closely thereof. So if you have some matrix that's broken down into P inverse dP, a to the n is going to be P inverse times d to the n P. And what happens is basically the left P inverse and the right P, when you have multiple a's multiplied together, they're going to cancel each other out repeatedly, leaving behind a d to the n in the center. And so if you do that to a matrix exponential, what ends up happening is that e to the ta is going to be P inverse e to the td times P. And e to the td is easy to compute because d is diagonal, or of Jordan normal form. In Jordan normal form, it's not quite diagonal, but it's like upper triangular usually. Or it's a very simple form. It's upper triangular, or maybe there's a 2 by 2 block if there's complex eigenvalues that you're hiding away somehow. It's significantly simpler. And so what you can then do actually is if you have that decomposition, you can actually even rewrite it again. You can rewrite dx dt p inverse dpx. You can reduce that to a diagonal system, or a close to diagonal system, where most of the different terms do not talk to each other, right? So since d is diagonal, or mostly diagonal, most of those terms in dy dt equals dy, those are just going to say, like, oh, the y1 term is going to talk to the y1 term. The y2 term is going to talk to y2. y3, maybe we had some complicated Jordan form, and now it also needs to consider y4. And likewise, y4 needs to consider y4 and y3. But it's never going to go too crazy, right? If you're looking at y5, you're not going to be seeing much. You're very unlikely to be interacting with y10 in any meaningful form. This form basically simplifies what is happening. Oh, I got a comment here. Yes, this linearization looks familiar. I think it is used to solve the harmonic oscillator in one dimension in quantum mechanics. Yeah, so that does tend to happen. So in quantum mechanics in general, what you have is you have some, I think it's usually denoted like psi. You have in quantum mechanics, you will have some sort of d psi dt, let me thicken my brush a little, is going to be equal to some sort of Hamiltonian of psi. And psi is usually some sort of state vector. And that state vector, and then you're going to have some psi 0 is equal to psi of 0, and then the solution of psi of t is equal to e to the t of h psi of 0. There might be some extra factor of, there might be an extra factor of I that I missed, but you can just append that on at the end, because the physicists love to do that thing where they add i's to operators to make things nice. But yeah, it's a similar idea. Now, what the physicists will hide sometimes is that H is not necessarily going to be a matrix per se. H just needs to be some sort of Hermitian. Actually, I can type this one out. H is just some Hermitian linear operator. Right, and that idea basically will carry over to, and Hermitian basically has some properties with the inner product of, you can move from one argument in an inner product to another without changing it. It might be anti-Hermitian. If you read a couple different books, they might have slightly different conventions. This is the one I think it is. I think it's supposed to be Hermitian. But do not quote me on that. Or maybe the I is with or without the Hermitian is. Anywho. But yeah, so it comes up a lot in this sort of form comes up a lot in quantum mechanics. Though it need not be a matrix. It could also be some sort of other generic linear operator, like a second derivative. That also happens. And in that case, you're dealing with more of like a heat equation type situation, or a oscillatory heat equation. Yeah, okay, self-adjoint, that sounds right, okay. Yeah. Trying to remember different physics conventions on the cuff is kind of difficult. But yeah, anyway. So yeah, we have a diagonalized system where most of the terms are just talking to itself, maybe a couple other terms. And so from that diagonalization, you can do a lot of, you can say a lot about its eigenvalues. The eigenvalues of A are going to transfer onto the eigenvalues of D. And so using those eigenvalues of D, you can get a very good understanding of the behavior of the system following those different eigenvalues lambda. And there are two main parts to it. So an eigenvalue is usually going to be some sort of complex number. It'll have a real component and it will have an imaginary component. The real component is going to dictate the growth of that term of the system. So if you have a real component, if you have a positive real component in your eigenvalue, solutions are going to grow in time. It'll be e to the 2t or e to the bt, where b is some positive real number, right? Positive exponentials like to grow. These are often called unstable nodes. In a similar fashion, if you have some negative value, so e to the negative at, if you have a negative real eigenvalue or real component to the eigenvalue, your solutions are going to decay, right? E to the negative RT or something, right? And that indicates a very fast and quick decay. And these are called stable. If you have some sort of imaginary component, it'll be e to the it. And e to the it, if you recall Euler's formula, is going to be cosine t plus I sine t. It oscillates. It goes back and forth, but it doesn't necessarily grow or shrink. And the magnitude of the imaginary, or the size of that imaginary component determines the frequency. So you have e to the 2it, you're going to have cosine of 2t, or sine 2t. And something that's sine of 2t is going to oscillate faster than something that's just e to the it, sine of t, cosine of t, however you want to call it. Right? It'll oscillate quicker as that imaginary component gets quicker. And fixed points, and these different fixed points that we sort of assumed that if you have a fixed point within a system, if we go back a few steps, right, those fixed points, the behavior of those fixed points can be characterized by the eigenvalues of that Jacobian matrix, right? So we have a fixed point, right? We have some fixed point at x naught, and we have some Jacobian matrix J. The eigenvalues of the Jacobian at that point x naught are going to dictate its overall stability of that point, right? Because if you have a fixed point, it means that dx dt is going to be equal to 0 at that point in particular. But if you get off of that point a little bit, you're going to get some response, and that response is going to be dictated by the eigenvalues. So now I'm going to review a number of these different combinations. So the nicest case is probably the stable fixed points. And the stable fixed points, in this case we have some two-dimensional system where both of the eigenvalues have negative real component. And if they have negative real component, if they're strictly real and are both negative, you're going to get a stable node. If the real component is negative, but it forms some complex conjugate pair, you're going to get a spiral, right? So if you have, so it'll either, if all real components are negative, it'll be nice and stable. And then the spirality of it is going to be dictated by if you have a complex conjugate pair. Likewise, if you have a pair of eigenvalues that are unstable or have positive real component, you're going to get an unstable node or an unstable spiral, depending on if you have a complex conjugate pair or not. There's not much to distinguish this other than the sign of that real component with those stable fixed points. And in a two-dimensional case, you can also get saddles, where you have mixtures of positive and negative real components. And that tends to be a fairly common situation that you'll see. You'll have some real component, you'll have some eigenvalue that's real and positive, and some eigenvalue that's real and negative, and then it will form this nice little saddle shape. The final example is you might have a complex conjugate pair of eigenvalues with a zero real component. So it'll be plus or minus I, plus or minus 5i, what have you. And that forms what is called a center. Now, these different graphs that I have here, I'm using to capture the different, directions of these spaces. So if you see here, the green indicates what is called the stable subspace. So basically things that will fall into the center. If you have a green circle, I've used that to indicate a stable spiral. So things are going to flow into it. Likewise, if you have an unstable system of some sort, you're going to have things flowing out and away from that manifold. If you just heard a chicken, you are not hallucinating. I will be dealing with him in the next coming days. So, you were so rude, dude. Anyway. Oh man, now I'm sorry. Yeah, so you can have unstable nodes and unstable spirals. Both of those I have indicated in red. You can have saddles, and if we see up here at the top, we have stuff flowing down towards the green and flowing out in that red direction. And then centers, sort of being between red and green, I have denoted with a yellow circle. And I believe, it's been a minute since I've put up these graphs, and I believe I have the length of the lines scaled in such a way to indicate the magnitude of the real part and of the frequencies. So you can have one example is the Lotka-Volterra system, which is do I have the equations now down? Is you have two fixed points, one at 0, 0, and one in this case at the point 1, 1. And those eigenvalues at those two different fixed points, they're two different fixed points. And so we can linearize about these two different fixed points. And so at this origin, linearizing about the origin, we have two eigenvalues, one positive, one negative, and we see when we see a saddle form, we have stuff flowing down the y-axis, and we see a bunch of stuff spiraling about it. Now, those spirals are not going to be necessarily perfect because the Lotka-Volterra system, if you are not aware, is a nonlinear system. It will take its own shape as you get farther away from these fixed points, but these two fixed points can already tell us a lot about how this system is expected to behave. I do apologize for the chicken. He will pay for it. A final important point to understand when dealing with linear systems is to understand what happens in a bifurcation. And a bifurcation is when fixed points change their color, basically, right? So I have these different fixed points of different colors, right? Red ones, green ones, yellow ones. And a bifurcation is basically what happens when a parameter change induces a change in that color or a change in that structure, right? So if you have something oscillating really fast and something oscillating really slow, that there's a quantitative difference between the two, but from a qualitative change, you can't really detect you're not really going to detect the difference, right? It's just going to spiral in, or it's going to spiral out, or it's just going to oscillate. However, if there's a change, right, it's instead of spiraling in, it starts spiraling out, that is called a bifurcation. And there are four main classes of bifurcation. There is a transcritical bifurcation, where two fixed points intersect at some particular parameter value, and they usually will swap the stability, right? So if you have a stable fixed point and an unstable fixed point, and they interact at some certain temperature, usually if you sort of track which one is which, usually they will swap stability between those 2 points. Another one is a saddle node fixed point, where out of nowhere you're going to get a pair of fixed points. One will usually be some sort of stable or unstable node, and the other one will be some sort of saddle. This can happen for a number of reasons. Temperature changes, or some birth rate has formed, or some parameter underlying the system has changed, and so the structure is now different. A pitchfork is basically what you get if you have a fixed point that changes stability and generates 2 new fixed points. It's sort of like a saddle node occurs on top of a pre-existing fixed point. And what happens is basically that fixed point gives off its stability or instability to 2 more fixed point, and it flips. The final one is a Hopf bifurcation, and Hopf bifurcations can be understood as basically a oscillating fixed point changes stability. So you can have an unstable spiral turning into a stable spiral, or vice versa. Those are the 4 main kinds of oscillations. And with that, that concludes today's seminar on compartment models and linear stability analysis. If you have any questions, feel free to leave a comment. If you like this video, then like this video. If you like this channel, then subscribe to it.